Well, welcome back to our course on system engineering. In this lecture and in this chapter, we're going to be talking about requirements analysis. And so just once again to remind us about where we are, this is the second chapter in the concept development. We have three major parts that we will be going through. The part one did a foundation and overview of that whole. Now we're getting a chance to go into some more details. So let's go ahead and get into some of the specifics here. First of all, let's talk about developing the system requirements. So another chapter we'll discuss in a lecture, we'll discuss the process of needs analysis, which is intended to provide a well-documented justification for initiating the development of a new system. The process also produces a set of operational requirements or objectives that describe what the new system must be designed to do, assuming that those responsible for authorizing the initiation of the system development have been persuaded that these primary requirements are reasonable and attainable within the constraints imposed by time, money, and other external constraints. The conditions have been achieved for taking the next step in the development of the new system. The principal objective of the concept exploration phase, as defined here, is to convert the operationally oriented view of the system derived in the needs analysis phase into an engineering oriented view required in the concept definition and subsequent phases of development. This conversion is necessary to provide an explicit and quantifiable basis for selecting an acceptable functional and physical system concept and then guiding its evolution into a physical model of the system. As in the case of operational requirements, the derivation of system performance requirements must also simultaneously consider system concepts that could meet them. However, to ensure that the performance requirements are sufficiently broad to avoid unintentionally restricting the range of possible system configuration, it is necessary to conceive not one, but to explore a variety of candidate concepts. New systems that strive for a major advance in capability over their predecessors or depend on the realization of a technological advantage require a considerable amount of exploratory research and development, that is R&D, before a well-founded set of performance requirements can be established. The same is true for systems that operate in highly complex environments and whose characteristics are not fully understood. For these cases, an objective of the concept exploration phase is to acquire the needed knowledge through applied R&D, that is research and development. This objective may sometimes take several years to accomplish, and occasionally these efforts prove that some of the initial operational objectives are impractical to achieve the required major revision. This discussion the discussion to follow shortly is generally available to all types of complex systems. For information systems in which software performs virtually all the functionality, a later chapter on software system engineering discusses software system architecture and its design and should also be consulted. Okay, let's go ahead and talk about the concept exploration phase in the system lifecycle. And we want to be thinking of the place of the concept exploration phase in that total system lifecycle. So the place of the concept exploration phase in the overall system development process is shown in this figure. It is seen that the top level system operational requirements come from needs analysis, which establishes that the needs are justified and that a development program is feasible within prescribed boundaries. The outputs of the concept exploration phase are a set of system performance requirements down to the subsystem level and a number of potential system design concepts that analysis indicates to be capable of fulfilling those requirements. While the formally defined concept exploration phase has a well-defined beginning and end, many of the supporting activities do not. For example, the exploratory development of advanced technological approaches, or the quantitative characterization of complex system environments often begin before and extend beyond the formal terms of this phase, being supported by independent research and development, IRAD, or other non-project funds. Additionally, considerable preliminary concept definition activities usually takes place well before the formal beginning of this phase. The specific content of the concept exploration phase depends on many factors, particularly the relationship between the customer and the supplier or developer, and whether the development is needs-driven or technology-driven. If the system developer and supplier are different from the customer, it is frequently the case in needs-driven system developments. The concept exploration phase is conducted in part by the customer's own organization or with the assistance of a systems engineering agent engaged by the customer. The focus is on its development of performance requirements that accurately state the customer's needs in terms that one or more supplier could respond to with specific product concepts. In the case of a technology-driven system development, the concept exploration phase is often conducted by the system developer and is focused on ensuring that the viable alternative courses of actions are considered before deciding whether or not to pursue the development of a new system. In both cases, a primary objective is to determine a set of performance requirements that can serve as the basis of the projected system development, and that have been demonstrated to ensure that the system product will meet all valid operational need. Well, next, let's consider the system's materialization status. And this is what we're looking at as a materialization and concept exploration phase. So the needs analysis phase was devoted to defining a valid set of operational objectives to be achieved by a new system, while a feasible system concept has visualized only as necessary to demonstrate that there was at least one possible way to meet the projected need. The term, quote, visualize is meant to connotate the conceptualization of the general function and physical embodiment of the subject, in this case of needs analysis at the subsystem level. Thus, in the concept exploration phase, one starts with a visual basis, generally on the above feasible concept. The degree of system materialization addressed in this phase has progressed to the next level, namely the definition of the functions that the system and its subsystems must perform to achieve the operational objectives, and to the visualization of the system's component configuration. And this is shown in the table that I'm sharing right now. So as you can see, we're now getting definition of the system down to the subsystem level. And as we're exploring this, let's also bring in the system engineering method in concept exploration and how it is applied there. So the activities in the concept exploration phase and their interrelationships are the result of the application of the system engineering method. So a brief summary of these activities is listed in the textbook, and we'll mention them here in this lecture. The names of the 4 generic steps in the method are shown. So first we have the operational requirements analysis. Also, you could call that requirements analysis. The typical activities include analyzing the stated operational requirements in terms of their objectives, restating or amplifying as required to provide specificity, independence, and consistency among different objectives, to assure compatibility with other related systems, and to provide such other information as may be needed for completeness. There's the performance requirements formulation, which is the functional definition. And typically the activities include translating operational requirements into system and subsystem functions and formulating the performance parameters required to meet the stated operational requirements. Then we have the implementation concept exploration, which is the physical definition. Typical activities include exploring a range of feasible implementation technologies and concepts, offering a variety of potentially advantageous options, developing functional descriptions and identifying the associated system components for the most promising cases, defining a necessary and sufficient set of performance characteristics reflecting the function essential to meeting the system operational requirements. We also have the performance requirements definition, which is dealing with the design validation. So typical activities include conducting effectiveness analysis to define a set of performance requirements that accommodate the full range of desirable system concepts, and validating the conformity of these requirements with the stated operational objectives and refining the requirements if necessary. So the interrelationships among these activities in these steps in the system engineering method are depicted in the flow diagram, which we'll be showing in 2 slides. So stay tuned. Let's talk about the requirements development and the sources that are used to make them. Requirements can originate from a variety of sources. The authors can rely on knowledge from existing system deficiencies, as well as evaluating novel concepts to derive requirements for the users to succeed in their future missions. A representative list of 4 types of approaches is offered in order to identify the diversity of requirement sources and to motivate the requirements developer to search for the right requirements development approach, depending on the starting point of the system and operational environment. So these are the things that we want to be thinking about. And so now let's go to this diagram that I mentioned. And so we'll see these 4 things discussed, but we're also can just be focusing on this context here in this flow diagram. In the first approach, the developer is given the chance to develop a new system that would operate in an environment against future threats. This may be a result of technology or concept breakthroughs that are ahead of the existing market and are constrained by the operational environment or selective threat conditions. The market may be very small and limited, and hence a great opportunity space is afforded the requirements developer. Some examples are from the physical sciences, such as space exploration or deep sea exploration, or other operation in extreme environmental conditions. Other examples may take a radically different approach to the existing problems, such as a commuter traffic that is conducted underground in enclosed tubes. Requirements sources may include visionaries or cutting-edge researchers that are both inventing capability and discovering them. The second approach is to improve existing systems based on their existing capabilities and deficiencies. This may originate from consumer demands to improve their capability or to respond to how the users intend to adapt the system use. This may often be found by crowdsourcing different ideas and to consider how the existing system will be improved or could be improved. Often a business case may be made if the consumer demand is large enough and is well documented to provide a good set of requirements. Many consumer goods would fall under this category. As the next model or next upgrade is rolled out to the consumer, often studying the previous feedback from the existing model. Third, the approach may require the system to be modified in response to a new threat. while operating. Often this comes about with military systems when operating against adversaries whose newer capabilities are discovered, necessitating a response in order to protect the users. Study of the deficiency of the existing system against the new threats is made in order to consider the solution space to adequately defend against the advanced threat. There is some risk in modifying the system to counter the exact threat, as it may mature into different capability. So the requirements analyst must look to forecast the likely range of threats to handle, especially if the acquisition and modification process is slower than the threat's rate of change. This may also occur to natural disasters that strike against existing systems and infrastructure, which necessitate a change in system, particularly if a great deal of damage and or loss of life has occurred. And finally, the fourth approach is creating additional systems to operate within the existing system. This may occur when allies or partnering organizations join forces to address a common problem. These new interoperability requirements may occur between systems, or it may be to modify the system's operators' behaviors or procedures. Often new system behavior may emerge from this new system modification, requiring additional constraints, procedures, and doctrine to be created to realize the benefit of the new system. New organization mergers that produce a modified system would be representative of this approach, such as international cooperation, for example, space exploration, joint military endeavors, or natural disaster responses that bring local, state, tribal, and federal emergency management forces together. So sources of new requirements may be visualized through use of the system context diagram, definition of the operational environment, threats and users, and other supporting systems and organizations. Through use of the approach listed above that we just spoke about, the creation of capability, interfaces, or additional system characteristics may help motivate the requirements engineer to explore the potential system configuration that would address the problem. Other sources of requirements may originate by extending the context diagram with additional users, such as maintainers, logistics, policymakers, allies, social, program officials, stakeholders, etc. By evaluating the system from different perspectives / users, additional requirements may be generated. Well, let's talk about requirements, features, and attributes. First of all, let's focus on the requirements features. A feature is a set of requirements that will satisfy an objective, which is typically at a higher level of abstraction. These may be identified more with potential users on the systems and envisions performance, which then may be decomposed to more specific requirements. An example of a feature is a vehicle that can support travel soccer game support. This feature may be composed of the following requirements. So we're seeing an example being laid out here. A vehicle can transport a minimum of 6 school-age children. The vehicle can transport a minimum of 10 soccer balls, 20 jerseys, and 2 games worth of snacks. The vehicle can support a minimum of 2 full-size coolers of food and beverages. And so these requirements may vary between, these features may vary between requirements, users, and their system's needs, but may be useful to organize sets of requirements in order to describe their performance to a set of specific users. Collections of these features can then be developed to ensure that the proper set of stakeholders have been adequately consulted to satisfy their specific needs. The features may also serve to ensure that conflicting or competing requirements are also identified and either negotiated, modified, or removed. Dependent features may also be analyzed to ensure that One requirement that is dependent on another requirement is considered in order to ensure a successful system requirement is developed. Next, let's talk about requirements attributes. There are selected attributes that may describe requirements which are common throughout the literature, much of which has been emphasized on the technical composition of the requirements, as in it is measurable, it is quantifiable, under what conditions and qualifiers is the requirement satisfied, etc. Often the quote SMART approach will accompany requirements: simple, measurable, attainable, realistic, and time-bound. So SMART, measurable, attainable, realistic, and time-bound. These attributes can determine whether the requirement is well written and stands a chance of accurately representing the system capability. Of equal importance is the approach on how the requirements are developed, how the document the requirements and updated, and maintaining configuration control. Numerous tools are available to maintain these requirements and to ensure that the work can be applicable to various portions of the system development effort. As requirements are verified and validated, these are also important attributes for the system engineer to ensure that the requirements will contribute to the successful system development effort. There are also good and bad examples of requirements that systems engineers should acquaint themselves with in order to emulate the successful requirements and to avoid the pitfalls of poorly developed requirements. Consider the example of public transportation system concept. We were talking a little about this before. Examples of good requirements are: the system shall be able to transport up to 20 passengers with a radius of 50 miles. Why is that good? It provides a measurable amount of passengers and operational radius, so the transportation system can be tested to see if it meets this requirement. The system shall provide a means of communication between its transport and the dispatch station to exchange health and status data of the transport system, exchanged every 15 minutes. Once again, why is this good? It provides a quantifiable means of describing the needed information to be exchanged. Note that it does not describe what type of format of message, nor does it presuppose the communication means. This is for the designer and systems engineering team to determine later. Well, let's look at examples of poor requirements. The system shall be able to operate in all weather. So why is this poor? Stating, quote, all weather implies that every imaginable weather condition would need to be satisfied for the transportation system. The system shall be diesel powered. Why is this poor? It states the design by using a diesel engine. How do we know that this is the correct solution, as there may be other alternatives? Requirements should describe what needs to occur, not how it should be built. The system shall use Volvo engines. Why is this poor? It presumes the solution. Human factors may also play into requirement development. Understanding the representative user and personnel that will come into contact with the system will greatly improve the chances of capturing a good set of human factor requirements. Research in the field, perhaps of the prototype, can also elicit requirements by observing interactions and human behavior while the prototype is being operated, and can also provide insight into what requirements were successful and which requirements may need improvement. Language may also be an issue, particularly if the system under development is not from the originating user country. Well, what are the characteristics of a well-stated requirement? As mentioned above, the requirement analysis process leads to a concise set of performance requirements. And so what we'll discuss here, and is in parallel to the section that we're relating to in the textbook, examines the challenges associated with specifically with translating operational requirements to performance requirements. Since operational requirements are first formulated as a result of studies and analyses performed outside a formal project structure, they tend to be less complete and rigorously structured than requirements prepared in a subsequent managed phases of the development and are mainly oriented to justify the initiation of the system development. Accordingly, in order to provide a valid basis for the definition of system performance requirements, their analysis must be particularly exacting and mindful of frequently encountered deficiencies such as a lack of specificity, dependence on a single assumed technical approach, incomplete operational constraints, lack of traceability to fundamental needs, and requirements not adequately prioritized. In an effort to cover all expected operational conditions and to, quote, sell the project, operational requirements are often overly broad and vague where they should be specific. In the case of most complex systems, it is necessary to supplement the basic requirements with a set of well-defined operational scenarios that represent the range of conditions that the system is required to meet. The opposite problem occurs if operational requirements are stated so as to be dependent on a specific assumed system configuration. To enable consideration of alternative system approaches, such requirements need to be restated to be independent of specific or, quote, point designs. Often operational requirements are complete only in regard to the active operational functions of the system and do not cover all of the constraints and external interactions that the system must comply with during its production, transportation, installation, and operational maintenance. To ensure that these interactions are treated as fully as possible at this stage of development, it is necessary to perform a life cycle analysis and to provide scenarios that represent these interactions. All requirements must be associated with and traceable to fulfilling the operational objective of the user. This includes understanding who will be using the system and how it will be operated. Compliance with the guidelines help to minimize unnecessarily or extraneous requirements. It also serves as a good communication link between the customer and developer when particular requirements subsequently lead to complex design problems or difficult technical trade-offs. The essential needs of the customer must be given top priority. If the needs analysis phase has been done correctly, requirements stemming from these needs will be clearly understood by all concerned. When design conflicts occur later in development, a review of these primary objectives can provide useful guidance for making a decision. Beyond the above primary or essential requirements, there are always those capabilities that are desired if they prove to be readily achievable and affordable. Requirements that are essential should be separately distinguished from those that are desired but not truly necessary for success of the primary mission. Often, preferences of the customer come through as hard and fast requirements when they are meant to be desirable features. Examples of desirable features, examples of desirable requirements are those that provide additional performance capabilities or design margin. There should be some indication of cost and risk associated with each desirable requirement so that an informed prioritization can be made. This discrimination between essential and desirable requirements and the prioritization is a key systems engineering function. Model-based system engineering, MBSE, can support good requirements definition by enforcing an organization's rules. For example, all requirements must be traced to an authoritative source, or all functional requirements must have an association with performance measurements. That is, what and how well. Model-based system engineering also supports collecting requirements by connections to system elements and not just by how they are organized or stored. This reduces the probability of a requirement being overlooked simply because it was misfiled. Well, continuing on, let's talk about the requirements development process. As in all phases of the system development process, the first task is to understand thoroughly and, if necessary, clarify and extend the system requirements defined in the previous phase. In this case, the operational requirements. In so doing, it is important to be alert for and avoid shortcomings that are often present in the operational requirements as initially stated. We use a general process known as requirements analysis to identify and discover performance requirements, synthesize and minimize initial set of requirements, and finally validate the final set of requirements. This requirements analysis occurs at each phase. However, the majority of effort occurs in the concept exploration phase, where operational requirements are transformed into system performance requirements with measurable thresholds of performance. These system performance requirements tend to be the basis for contractual agreements between customer and developer, and therefore need to be accurate and concise. We'll show this figure in a minute on the next slide, but it depicts the general process for developing requirements. Of course, this would be tailored to a specific application. The first activity involves the creation of a set of requirements. It is rare this occurs out of whole cloth. Typically, a source of needs exists. In the concept exploration phase, a set of operational needs and requirements have been established. However, those needs and requirements are typically expressed in the language and context of the operator or users. These must be translated into a set of system-specific requirements describing its performance. Well, here is the figure that I just mentioned before, and this is a simple requirements development process, and we'll use this as a backdrop as we talk about some other aspects of requirements development. First, let's talk about requirements elicitation. When analysts are developing operational requirements, they rely heavily on input from users and operators, typically through market surveys and interviews. When analysts are developing performance requirements, they rely on both people and studies, initially the customer or buying agent within an organization is able to provide thresholds of affordability and levels of performance that are desirable, but subject matter experts, SMEs, can also provide performance parameters as a function of technology levels, cost, and manufacturability. Previous studies and system development efforts can also assist in determining performance requirements. And finally, a requirement analyst performs a system effectiveness analysis to provide insight into the level of performance needed. All of these sources provide the analyst with an initial set of performance requirements. Many times, however, this set of requirements contains inconsistencies or even dichotomies. Further, many requirements are redundant, especially when they come from different sources. So the analyst must conduct a synthesis to transform an initial set of requirements into a concise, consistent set. A useful approach to developing requirements of any type is to ask the 6 interrogatives: who, what, where, why, when, and how. Of course, different types of requirements focus on different interrogatives. Operational requirements focus on why, defining the objectives and purpose of the system. Performance requirements focus on the what, defining what the system shall do and how well. Next, let's talk about the requirements analysis. This activity starts with an initial set of requirements from the elicitation stage. Individual requirements, as well as the set as a whole, are analyzed for various attributes and characteristics. Some characteristics are desirable, such as feasible and verifiable. Other characteristics are not, such as vague or inconsistent. For each requirement, a set of tests, that is, or questions, is applied to determine whether the requirement is valid. And while many tests have been developed by numerous organizations, we present a set of tests that at least form a baseline. These tests are specific to the development of system performance requirements. So one is a requirement traceable to a user need or operational requirement. Two is a requirement redundant with any other requirement. Three is a requirement consistent with other requirements. Note, requirements should not contradict each other or force the engineer to an infeasible solution. Four, is a requirement ambiguous and not subject to interpretation? Is a requirement technologically feasible? 6, is the requirement affordable? 7, is a requirement verifiable? If the answer to any of these questions above is no, then the requirement needs to be revised or possibly omitted. In addition, other requirements may need to be revised after performing this test. In addition to individual requirements test, a collective set of tests is also performed, usually after the individual test has been performed on each requirement. So one, does the set of requirements cover all of the user needs and operational requirements? Two, is the set of requirements feasible in terms of cost, schedule, and technology? Three, can the set of requirements be verified as a whole? Both type of tests may need to be iterated before a final set of performance requirements exists. Next, we want to be looking at the requirements validation. Once a set of performance requirements are available, the set needs to be validated. This may be accomplished formally or informally. Formal validation means using an independent organization to apply various validation methods to validate the set of requirements against operational situations. For example, that is scenarios and use cases, and determine whether the requirement embodied within a system concept could achieve the user needs and objectives. Informal validation at this point means reviewing the set of requirements with the customer and/or users to determine the extent and comprehensiveness of the requirements. After that, let's look at the requirements documentation. A final important activity is the documentation of the performance requirements. This is typically accomplished through the use of an automated tool such as doors. If you haven't heard of that, you can just look that up with it via an internet search. Many tools exist that manage requirements, especially large, complex requirements hierarchies. As system complexity increases, the number and types of requirements tend to grow, and using simple spreadsheet software may not be sufficient to manage requirements databases. Next, let's consider the incompatible operational requirements. It should be noted that a given set of operational requirements does not always lead to feasible performance characteristics. Earlier, the automobile was mentioned as a system that was required to undergo significant changes because of government-imposed regulations concerning safety, fuel economy, and pollution control. Initially, these areas of regulation were independently developed. Each set of requirements was imposed solely on the basis of a particular need, with little regard for either the associated engineering problems or other competing needs. When these regulations were subjected to the engineering analysis, it was shown that they were not collectively feasible within the practical technology available at the time. Also, the investment in development and production would result in a per unit cost in excess of the current automobile prices. The basic reason for these problems was the available pollution controls necessary to meet emission requirements resulted in lower fuel economy, while the weight reduction necessary to meet the required fuel economy defeated the safety requirements. In other words, a three independent set of operational requirements turned out to be incompatible because no one had initially considered their combined impact on the design. Note that in this instance, an analysis of the requirements did not depend on the detailed design system, since simply examining the design concepts readily revealed the conflicts. So we can consider example. So let's consider the concept of a new aircraft. So as an instructive example of a concept exploration, we could illustrate this by looking at the acquisition of a new commercial aircraft. So assume for discussion that an airline companies serve short to medium domestic routes using two-engine propeller-driven aircraft. Many of the airports it serves have relatively short runways. This arrangement has worked well for a number of years. The problem is that has become more and more apparent is that because of increasing maintenance and fuel expenses, the cost per passenger mile has increased to the point where the business is marginally profitable. This company is therefore considering a major change in its aircraft. In essence, the airline needs to lower the cost per passenger mile to some acceptable value and to maintain its competitive edge in short route services. The company approaches several aircraft manufacturers for preliminary discussion of a new and modified airplane to meet its needs. This discussion indicates that there are several options available. Three such options are: one, a stretched aircraft body and increased power. Engines of the appropriate form and fit exist for such a configuration. This option permits a quick, relatively low cost upgrade, which increases the number of passengers per aircraft, thereby lowering the overall cost per passenger mile. Two, a new larger four-engine propeller aircraft using state-of-the-art technology. This option offers a good profit return in the near term. It is reasonably low risk, but the total useful life of the aircraft is not well understood and growth potential is limited. Three, a jet-powered aircraft that is capable of takeoff and landing at most, but not all, necessarily all of the current airports being served. This option permits a significant increase in passengers per aircraft and opens up the possibility of competing for new, longer routes. This is also the most expensive option because of the inherent lower maintenance and fuel costs of jet engines relative to propeller engines. Operating costs for the aircraft are attractive, but some existing routes will be lost. It is evident that the final choice will require considerable expenses and should be based on a competitive competition among interested manufacturers. The airline engages a services of an engineering consulting company to help its staff prepare a set of aircraft performance requirements that can serve as the basis for the competitive bids and to assist in the selection process. In exploring the above and related options, the alternative functional approaches are considered first. These appear to center on the choice between staying with propeller engines, an option that retains the basic features of the present aircraft, or moving to jet engines, which offer considerable operational economies. However, the latter is a major departure from the current system and will also affect its operational capabilities. To permit this choice to be left open to the bidders, the performance requirements such as the runway length, cruising speed, and cruising altitude will need to be sufficiently broad to accommodate these two quite different functional approaches. Okay, let's next talk about the requirements hierarchy. And so we have several levels, and we'll stay on this chart to discuss them. So first of all, requirements are organized into several different levels in order to assist the requirements engineer a means to develop the requirements for the proper scope. For the purpose of these lectures and what's in the textbook, we organize these requirements into operational, system, performance, and components. Each requirement level can provide information to different users as well as to guide the system and concept development. In addition, the linkage between the different levels must be defined as well in order to quantify how requirements from lower levels contribute to the successive levels. Okay, well, let's go ahead and talk about these in a little bit more detail one at a time. And so first of all, operational requirements. Operational requirements are described by what needs to execute within the scope of the operations. These requirements are generally less quantified and higher in level of detail. Users and stakeholders' perspectives play a larger role in the shaping these requirements and often describe the requirements in their own words or terminology. It is critical to capture the correct set of users to develop these requirements types in order to represent the scope of the stakeholders. Operational requirements must initially be described in terms of operational outcomes rather than system performance. They must not be stated in terms of implementation nor biased towards a particular conceptual approach. All requirements should be expressed in measurable, that is, testable terms in case the new system is required to use substantial portions of an existing system that should be specifically stated. The rationale for all requirements must be stated or referenced. It is essential for the system engineer leading the systems development to understand the requirements in terms of what of user needs so that inadvertent ambiguities do not result in undue risk or costs. The time at which a new system needs to be available is not readily derived from purely operational factors, but may be critical in certain instances due to financial factors, obsolescence of current systems, schedules of system platforms, for example, ships and bases, and other considerations. This may place constraints on system development time and hence on the degree of departure from the existing system. Hence, the initially stated operational requirements for a new system are seldom based on an exhaustive analysis. It should be understood by both the customer and potential developer that these requirements will be refined during the development process as further knowledge is gained concerning the system's needs and operating environment. So from this above consideration, it is seen that work carried out during the analysis phase must be regarded as preliminary. Subsequent phases will treat all system aspects in more detail. However, experience has shown that the basic concept approach identified during needs analysis often survives into subsequent phases. This is to be expected because considerable time and effort is usually devoted to the process, which may last for 2 or 3 years. Even though only limited funds are expended, many organizations often get involved. Okay, so we talked about operational requirements. Let's talk about the system level requirements. And so system level requirements are more focused on the system and how it performs in the operational environment. May also be concerned with the supporting infrastructure as well as other systems that it may come into contact with during expected operations. System level requirements will likely focus on quantitative metrics and how the system will perform within the environment. Different perspectives may be garnered from using a context diagram or other ways to look at the system in a holistic manner in order to ensure completeness with the requirements. Being able to conceptualize the system within the environment can also identify additional requirements such as interfaces or behaviors in response to friends or foe during the envisioned system objective. Also included within aspects of the system such as maintenance, repair, disposal, training, etc., may also identify additional requirements that should be considered from a systems perspective. Well, let's consider the system lifecycle scenario to understand all of the situations that a system will encounter during its lifetimes. It is necessary to develop a model or scenario that identifies all of the different circumstances which the system will be exposed. These will include at least one, storage of the system and or its components. 2, transportation of the system to its operational site. 3, assembly and readying the system for operation. 4, extended deployment in the field. 5, operation of the system. 6, routine and emergency maintenance. 7, system modification and upgrades. And 8, system disposal. The model of these phases of the system's use must be sufficiently detailed to reveal any interactions between the system and its environment that will affect its design. For example, the maintenance of the system will require a supply of spare parts, specialty test equipment, special test points, and other provisions that need to be recognized. Only by visualizing the complete life of the projected system can we validate requirements and associated costs by being developed. Okay, we have the performance requirements formulation. So as noted above, in the course of developing a new system, it is necessary to transform the system operational requirements, which are stated as required outcomes of the system action, into a set of system performance requirements, which are stated in terms of engineering characteristics. This step is essential to permit subsequent stages of system development to be based on and evaluated in engineering rather than operational terms. Thus, the system functional performance requirements represent the transition from operational to engineering terms and reference. So with that, now we're moving on to the performance level requirements. In deriving performance requirements from operational objectives, it is first necessary to identify the major functions that the system must perform to carry out the prescribed operational actions. That means, for example, that a system is needed to transport passengers to such destinations as they wish along existing roadways, and functional elements must include, among others, a source of power, a structure to house the passengers, power transmitting interface with the roadway, and an operator activated control of locomotion and direction. Expressed in functional terms, that is verb object, these elements must be called power vehicles, house passengers, transmit power to roadway, control locomotion, and control direction. A beginning in this process has already been made in the preceding phase. However, a more definitive approach is needed to establish specific performance parameters. During this phase, the functional definition needs to be carried a step further, that is, to a definition of the subsystem functions and to the visualization of the functional and associated physical components, which collectively can provide these subsystem functions. Then part of this third element, we want to be thinking about the non-deterministic nature of the system development. The derivation of performance requirements from desired operational outcomes is far from straightforward. This is because like other steps in system materialization process, the design approach is inductive rather than deductive, and hence not directly reversible. And going from the more general operational requirements to the more specifically defining system performance requirements is necessary to fill in many details that were not explicitly called out in the operational requirements. This can obviously be done in a variety of ways, meaning that more than one system configuration can, in principle, satisfy a given set of system requirements. This is also why in the system development process, the selection of the, quote, best system design at a given level of maturation is accomplished by trade-off analysis using a predefined set of evaluation criteria. The above process is exactly the same as that used in inductive reasoning. So, for example, in designing a new automobile to achieve an operational goal of 600 miles on a tank of gasoline, one could presumably make an engine extremely efficient or give it a very large gasoline tank or make the body very light, or some combination of these characteristics. Which combination of these design approaches is selected would depend on the introduction of other factors such as relative cost, development risk, passenger capacity, safety, and many others. This process can be understood by considering a deductive operation, as for example, performance analysis giving a specific system design. The system's performance may be deduced unambiguously from the characteristics of the components by first breaking down components' function, then calculating their individual performance parameters, and finally aggregating these into measures of the performance of the system as a whole. The reverse of this deductive process is therefore inductive and consequently non-deterministic. One can see from this preceding discussion that given a set of operational requirements, there is no direct, that is, deductive method of inferring a corresponding unique set of system performance characteristics that are necessarily insufficient to specify the requirements for a system to satisfy the operational needs. Instead, one must rely on experience-based heuristics and, to a large extent, a trial and error approach. This is accomplished through a process in which a variety of different system configurations are tentatively defined. Their performance characteristics are deduced by analysis or data collection, and these are subjected to effectiveness analysis to establish those characteristics required to meet the operational requirements. So as a part of this, we have to be considering the formulation of performance characteristics. So as noted before, the objective of the concept exploration phase is to derive a set of system performance characteristics that are both necessary and sufficient. This means that the system possessing them will satisfy the following criteria. One, a system that meets the system operational requirements and is technically feasible and affordable will comply with the performance characteristics. Two, a system that possesses these characteristics will meet the system operational requirements and be designed to be technically feasible and affordable. The condition that the set of performance requirements must be necessary as well as sufficient is essential to ensure that they do not inadvertently exclude a system concept that may be especially advantageous compared with others, just because it may take an unusual approach to a particular system function. This often happens when the performance requirements are derived in part from a predecessor system and carry over features that are not essential to its operational behavior. It also happens when there is a preconceived notion of how a particular operational action should be translated into a system function. For the above reasons, the definition of performance characteristics needs to be an exploratory and iterative process, as shown in the previous figure. I'll pull that up in just a second. In particular, if there are alternative functional approaches to an operational action, they should all be reflected in the performance characteristics, at least until some may be eliminated in the implementation and validation steps in the process. So let me go ahead and go back to that chart, and just so you can have an idea. So this is the chart that I'm referring to. You can go ahead and just pause this and stay on that chart for a little while if you would like. So for the requirements formulations by the integrated product teams, or IPTs, so as we were talking about earlier, the responsibility for defining the performance requirements of a new product is thus that of the customer, or in the case of government programs, that of the acquisition agency. However, the organization of the process and its primary participants vary greatly with the nature of the product, the magnitude of the development, and the customer auspices. A recent practice introduced by the Department of Defense is the use of the integrated product teams, or IPTs, throughout the acquisition process. IPTs are intended to bring a number of benefits to the process. They bring senior industry participants into the system conceptual design process at the earliest opportunity, therefore educating them in the operational needs and injecting their ideas during the formative stages of the development. Two, they bring together the different disciplines and specialty engineering viewpoints throughout the development. Three, they capitalize on the motivational advantages of the team collaboration and consensus building. Four, they bring advanced technology and COTS, commercial off-the-shelf technology, to bear on the system design approaches. As in the case of any organization, the success of the approach is highly dependent on the experience and interpersonal skills of the participants, as well as on the leadership qualities of the persons responsible for the team organization. And perhaps even more important is the system engineering experience of the team leaders and members. Without this, the majority of the team members, who tend to be specialists, will not be able to communicate effectively, and hence the IPT will not achieve its objectives. So continuing on, thinking about the performance level requirements process, component level requirement, I'm finishing up with that and now moving on to the component level requirements. So the component level requirements are focused on the technical aspects of the system and will at the lower level of the technical details. And these requirements may also be concerned with the design aspects in order to ensure that the performance criteria are met. Similar to the system level requirements, these are highly quantitative in nature and will come with some expected performance under defined conditions. Reliability may also be focused on the component level in order to determine if the entire system reliability numbers are achievable. Specifications are developed at the next step from the component level requirements in order to guide manufacturing with the desired level of performance and precision while constructing the components. Each phase of development must begin with a detailed analysis of all the requirements and other terms of reference on which the ensuing program is to be predicated. In terms of problem solving, this is equivalent to first achieving a complete understanding of the problem to be solved. So this includes an analysis of stated performance requirements. So requirements analysis in a concept definition phase is especially important because system performance requirements, as initially stated, often represent an imperfect interpretation of the user's actual needs. Even though the previous phase may have been thoroughly carried out, the derivation of the set of performance requirements for a complex system is necessarily an imprecise and often subjective process. Not to mention iterative. In particular, the stated requirements tend to be influenced by personal and often not well-founded assumptions of what will turn out to be hard or even easy to achieve. This may result in some performance requirements being unnecessarily stringent because they are believed to be readily achievable, a presumption that may turn out to be invalid. It is therefore essential that both the basis for the requirements and their underlying assumptions be clearly understood. Following this, steps can be taken to refine the requirements as necessary to support the definition of a truly viable system concept. The estimated relative difficulty of achieving the requirements will help to guide resource allocation during the development. The task of understanding the source of the given performance requirements in terms of user needs is in particular province of system engineering. This task requires an intimate acquaintance with the operational environment and with systems users as circumstances may permit. In the case of complex operational systems, such as understanding Such an understanding can be derived through years of work in the field. Next, we have categories of system requirements. In discussing the subject of requirements analysis, attention is usually focused on what functions the system must perform and how well. So we have named these types of well-defined requirements as functional and performance. There are, however, other types of requirements that may be much more poorly defined or even omitted in this phase. These include one, compatibility requirements, how the system is to interface with its operating site, its logistic support, and other requirements. Reliability, number two, reliability, maintainability, and availability, or RMA requirements. How reliable the system must be to fulfill its purpose, how it will be maintained, and what support facilities will be required. And then three, environmental requirements. What extremes of the physical environment must a system be built to withstand throughout its lifetime? So RMA, like we mentioned, reliability, maintainability, and availability requirements, when explicitly stated, tend to be arbitrary and often not well defined. For the other two categories, requirements are often largely confined to the system's operational mode and leave out the conditions of shipping, storage, transit, assembly, and supporting the system. In these circumstances, it is necessary to investigate in detail the entire life of the system from product delivery to the end of its operational life and disposal. We also have completion and refinement of system requirements. We need to be thinking about that. So the development of a system lifecycle model will almost always reveal that many important system requirements were not explicitly stated. This is likely to be true not only for non-operating phases of the system, but also for the interaction with the physical environment. These environmental specifications are often derived from boilerplate rather than from a realistic model of the operating environment. In contrast, the desire to make use of standard commercial components may cause such specifications to be unduly relaxed or omitted entirely. Probably the most important requirement that is often not stated is that of affordability. In competitive system developments, the projected system cost is one of the factors considered in selecting the winning proposal. Therefore, affordability must be considered equivalent to other stated requirements, even though it may not be represented as such. It is therefore necessary to gain as much insight as practicable into the level of projected system costs. Development, production, and support will constitute an acceptable or competitive value. Useful life is another system characteristic that is seldom stated as a requirement. To prevent early obsolescence, a system that uses high technology must be capable of periodic upgrades or modernization. To make such a process economically viable, the system must be designed with the objective in mind, making those subsystems or components that are susceptible to early obsolescence easy to modify or replace with newer technology. In some programs, such upgrades or growth capacity is explicitly provided for. The process is sometimes called pre-planned production improvements, P3I. In the majority of cases, however, especially when initial cost is a major concern, there is not a stated requirement for such capability. Nevertheless, it must be kept in mind as an important criteria for comparing alternative system concepts, since in practice, future changes in operating conditions and/or system environments or production competition will more often than not lead to increased pressures for a system upgrade. Well, what about unquantified requirements? We're getting a tour of a lot of different requirements. We focused on these four major areas. In order to be useful, a system requirement must be verifiable. This typically means measurable. When the requirement is stated in non-quantifiable terms, the task of requirements analysis includes the endowment of it with as much quantifications as possible. So we have two examples here we can be thinking about. A commonly unqualified area. First, a commonly unqualified area is that of user requirements, and especially the user system interface. The overworked term user-friendly does not translate readily into measurable form. Accordingly, it is important to gain a first-hand understanding of the user's needs and limitations. This in turn is complicated by the fact that there may be several users with different interfacing constraints and levels of training. There is also the maintenance interface, which has totally different requirements. The interfaces between the system and other equipment at its operating site and with related systems are also often not stated in measurable terms. This may require a first-hand examination of the projected system environment and even measurements of these interfaces if necessary. For example, are there specifications for such parameters as available power or input signals that must be provided at the site? Well, what about the requirements in the predecessor system? As noted previously, if there is a predecessor or the current acting system that performs the same or similar function as a projected system, as is usually the case, it is the single richest source of information on the requirements for the new system. It deserves a detailed study by system engineering at all stages of development, especially the formative phases. The predecessor system often offers an excellent basis for understanding the exact nature of the deficiencies that led to the call for a new system. Since all the attributes are measurable, they can serve as a point of departure for quantifying the requirements for the new system. There's frequently documentation available that can provide a direct comparison to requirements for the new system. The users of the predecessor system are usually the best source of information of what is needed in a new system. Thus, system engineering should make an effort to gain a detailed firsthand understanding of the system operation. And then what about operational availability? There may or may not be stated requirements for the date at which the system is to be ready for operational use. When that is it important to try to understand the priority of the meeting with the date relative to the importance of development cost, performance, and other system characteristics. This knowledge is needed because these factors are mutually interdependent and their proper balance is essential to the success of the system development. In any event, the time of availability is always important to the ultimate value of the system. This is because the growth of technology and competitive pressure operate continuously to shorten the new system's effective operational life. Thus, the time of operational availability must be considered a prime factor in the planning of a system development. In commercial developments, the first product to exploit a new technology often gains a lion's share of the market. Okay, and then one final area that we'll cover for this chart is considering determining the customer/user needs. So as we noted earlier, it is always necessary to clarify, extend, and verify the stated system requirements through contact, not only with the customer, but also with present users of the existing or similar systems. In a competitive acquisition program, access to the customer may often be formally controlled. However, it should be used insofar as possible to clarify ambiguities and inconsistencies in the requirements as originally stated. This may be done directly through correspondence or at a bidders conference as appropriate. A better opportunity to clarify system requirements is in the pre-proposal stage. In many large acquisition programs, a draft request for proposal, RFP, is circulated to prospective bidders for comments. Usually this period is usually possible to obtain better understanding of the customer requirements that will be possible after the issuance of the RFP. This emphasizes the fact that the effort to respond to a system acquisition RFP must begin well before, that is, months or years before its formal issuance. In developing commercial systems, there is always an active and often an extended market survey to establish customer/user needs. In these cases, explicit system requirements may often not yet exist. As a prerequisite to the definition of a system concept and its associated performance requirements, it is therefore essential that system engineering interact as directly as possible with potential customers and users of current systems to observe at first hand the system strengths, limitations, and associated operating procedures. Well, next, let's talk about requirements metrics. How do we come to an assessment of whether something is performing well and whether we're satisfied? And thus, for this chapter, we're thinking in terms of the requirements, whether we've got a good requirement. Metrics are used to inform the analyst, engineer, and decision maker whether or not the system will successfully accomplish the intended objective while in an operational environment under operational conditions. Metrics may also be consulted while performing system analysis to estimate if the envisioned system concept will be successful or not based on the value of the metric. Metrics may also provide a sense of a goal for the developers to design a system that will meet these metrics, which may describe the capabilities from the system down to the component. Metrics may be used by numerous users. Concept designers will use metrics to envision the desired performance of the new system concept and gauge its contributions to the environment. Requirements analysis will use metrics to evaluate the system concept within their models and simulation. Test engineers will use metrics to evaluate whether the test on the selected system was successful or not. So let's consider measures of effectiveness, MOE, and measures of performance, MOP. With the introduction of operational effectiveness analysis, we need to explore the concept and measuring of certain metrics. Metrics are key to ultimately defining the system, establishing meaningful and verifiable requirements, and testing the system. Therefore, defining these metrics appropriately and consistently through the development lifecycle is essential. Many terms exist to describe these effectiveness and performance metrics. Two commonly used and ones we will use throughout this book and what we're going to have in our lectures are measures of effectiveness, MOE, and measures of performance, MOP. Unfortunately, no universal definition exists for these terms, but the basic concept behind them is crucial to understanding and communicating a system concept. So for measures of effectiveness, a quantitative or qualitative or quantitative metric of a system's overall performance that indicates the degree to which it achieves its objectives under specified conditions. And MOE always refers to the system as a whole. For measures of performance, MOP, a quantitative metric it's a quantitative measure of the system's characteristics or performance of a particular attribute of a subsystem. And MOP typically measures a level of physical performance below that of the system as a whole. Regardless of the definition one uses, it is a universal axiom that an MOE is superior to an MOP. In other words, if the two are placed in a hierarchy, MOEs is always above MOPs. Typically, an MOE or MOP will have three parts: its metrics, its units, and the conditions or context under which the metric applies. For example, an MOE of a new recreational aircraft would be maximum range in nautical miles at sea level on a standard atmospheric day. The metric is maximum range. The units are natural nautical miles, and the conditions are a standard atmospheric day, which is well defined at sea level. This MOE relates to an aircraft as a whole and describes one aspect of its performance in achieving the objective of aerial flight. MOEs can be of many forms, but we can define three general categories: measurements, likelihood, or binary. Measurements is an MOE that can't be directly measured either from an actual system, subsystem, or mathematical or physical model. It may be deterministic or random. Likelihood MOEs correspond to a probability of an event occurring and may include other MOEs. For example, a likelihood MOE could be the probability of an aircraft achieving a maximum altitude of 20,000 feet. In this case, a likelihood is defined in terms of another measurement of MOE. Finally, a binary MOE is a logical variable of the occurrence of an event. Either the event occurs or not. When an MOE is measured or determined, we call the resultant measure the value of the MOE. Thus, in an aircraft example, if we measure the maximum range of the new aircraft as 1675 nautical miles, then 1675 is the value. Of course, MOEs, as any metrics, can have multiple values under different conditions. Finally, engineers use binary MOEs to determine whether a particular characteristic of a system exceeds a threshold. For example, we would define a threshold for maximum range of an aircraft as 1,500 nautical miles at sea level as a standard day. A binary MOE could then be defined to determine whether a measured value of the MOE exceeds our threshold. For example, the binary MOE would be yes, our measured value of 1675 nautical miles exceeds our thresholds of 1,500 nautical miles. Well, next, let's talk about requirement verification and validation. Having derived the operationally significant performance characteristics for several feasible alternative concepts, all of which appear to be capable of meeting the system operational requirements, the next step is to refine and integrate them into a singular set to serve as a basis for the preparation of formal system performance requirements. As stated earlier, these performance requirements stated in engineering units provide an unambiguous basis for the ensuing phases of system development, up to the stage where the actual system can be tested in a realistic environment. The operations involved in the refinement and validation of the system performance requirements can be thought of as two tightly coupled processes: an integration process, which compares and combines the performance characteristics of the feasible alternative concepts, and an effectiveness analysis process, which evaluates the validity of the integrated characteristics in terms of the operational requirements. So we'll talk about three specific things as we're talking about this verification and validation process. First, let's talk about the performance characteristics integration. So the integration process serves to select and refine those characteristics of the different system concepts examined in the exploration process that are necessary and sufficient to define a system that will possess the essential operational characteristics. Regardless of an analytical tools that may be available, this process requires the highest level of system engineering judgment. This and other processes in the phase can benefit greatly by the participation of system engineers with experience with the predecessor system, as mentioned previously. The knowledge and database that comes with the system is an invaluable source of information for developing new requirements and concepts. And in many cases, some of the key engineers and managers who directed its development may still be available to contribute to the development of new requirements and concepts. They may not only be aware of the current deficiencies, but are likely to have considered various improvements. Additionally, they are probably aware of what the customer really wants based on their knowledge of operational factors over a number of years. Just one key system engineer with this background can provide significant help. Experienced people of this type will also have an educated, quote, gut feel about the viability of the requirements and concepts that are being considered. Their help, at least as consultants will not alleviate the need for requirements analysis, but it may quickly point the effort in the right direction and avoid blind alleys that might otherwise be pursued. Next, let's talk about the performance characteristics validation. The final step in the process are to validate the derived performance characteristics against the operational requirements and constraints, and to convert them into the form of requirements document. Ideally, the performance characteristics derived from the requirement step will have been obtained from concept validation in the implementation concept exploration process. However, it is likely that the effort to remove irrelevant or redundant characteristics in the integration step and to add external constraints not present in the effectiveness model will have significantly altered the resultant set of requirements. Hence, it is essential to subject them once more to an effectiveness analysis to verify their compliance with the operational requirements. The effectiveness model in the above step should generally be more rigorous and detailed than models used in previous steps so as to ensure the final product does not contain deficiencies due to omissions of important evaluation criteria. The above process operated in closed loop fashion until a self-consistent set of system performance characteristics is obtained that meets the following objectives. So first, they define what the system must do and how well, but not how the system should do it. Two, they define the characteristics of in engineering terms that can be verified by analytical means or experimental tests so as to constitute a basis for ensuring engineering phases of system development. And three, they completely and accurately reflect the system operational requirements and constraints, including external interfaces and interactions, so that if a system possesses the state characteristics, it will satisfy the operational requirements. And third and finally, for this section, the requirement documentation. To convert the system performance characteristics into a requirements document involves skillful organization and editing. Since the system performance requirements will be used as a primary basis for the ensuring concept definition phase and its successors, it is the most important that the document be clear, consistent, and complete. However, it is equally important to recognize that it is not carved in stone, but is a living document which will continue to evolve and improve as the system is developed and tested. And a needs-driven system development in which it is intended to compete the concept definition phase among a number of bidders, the system performance requirements are primarily components of the competitive solicitation, along with a complete statement of all other conditions and constraints. Such a solicitation is often circulated in draft form among potential bidders to help ensure its completeness and clarity. And a technology-driven system development in which the same commercial company that will carry out the definition and subsequent phases conducts the exploratory phase, the end product typically serves as a basis for deciding whether or not to authorize and fund a concept definition phase preliminarily to the engineering development. For this purpose, the requirement document typically includes a thorough description of the most attractive alternative concepts investigated, evidence of their feasibility, market study validating the need for a new system, and the estimates of a development, production, and market introduction cost. Okay, the final thing that we'll cover here is requirements development, considering traditional system engineering versus agile. Traditional system engineering, or TSE, will often take a waterfall approach towards developing new requirements, ensuring that the appropriate stakeholders have been consulted, considering the various operational environment and future threats for which the new system will be designed for is adequate. The approach can often be more time-consuming as it may look at more of a strategic approach in order to evaluate the new system concept and its envisioned contribution into the environment. Agile system engineering will often take a quicker development approach towards requirement development. They will also consult the stakeholders, but this may require an iterative approach in order to develop portions of the system requirements and may focus on selected parts and perspectives of the system while gaining feedback from the various stakeholders. Because of this approach, they may take a more bottoms-up perspective towards the system and may look at the tactical view of the requirements of the system and its requirements. Well, let's finish up this chapter and this lecture with a summary review. And so we'll go over the major items that we talked about. First, the developing the system requirements. The objective of the concept exploration phase are to explore alternative concepts to derive common characteristics and convert the operationally oriented system view into an engineering oriented view. Outputs of the concept exploration are 1, system performance requirements, 2, a system architecture down to the subsystem level, and 3, alternative system concepts. Activities that comprise concept exploration are operational requirements analysis, which look at ensuring completeness and consistency. Implementation concept exploration, which explores refining functional characteristics. Performance requirements formulation, which involves deriving functions and parameters. And performance requirements validation, which involves ensuring operational validity. Next, we talked about requirements development and sources. Requirements can originate from a variety of sources. The authors can rely on knowledge from existing system deficiencies, as well as evaluating novel concepts to derive requirements for the user to succeed in their future missions. 4 general approaches include developing of a new system to operate in a future environment, usually as a result of new technology or concept. So that's next. We have improvement. Given the existing system, consumer demand can identify new ways to improve the existing system. Threat-driven, new threats require re-examination of existing systems and concepts with improvements to counter these threats. In addition, new allied or complementary systems are introduced, enhancing the original system, but requires a new way to interface and operate. Next, we talked about requirement features and attributes. A feature is a set of requirements that will satisfy an objective, which is typically at a higher level of abstraction. These features may vary between requirements users and their system needs, but may be useful to organize sets of requirements in order to describe the performance to a set of specific users. Collections of these features can then be developed to ensure that the proper set of stakeholders have been adequately consulted to satisfy their specific needs. Requirements attributes describe the technical composition of the requirements. Is it measurable? Is it quantifiable? Under what conditions? And qualifiers, is this requirement satisfied, etc. We went through the requirements development process. Requirements development involves 4 basic steps: elicitation, analysis, validation, and documentations. These steps will, done correctly, lead to a robust set of well-articulated requirements. We talked about requirements hierarchy. Requirements are organized into several different levels in order to develop the requirements for the proper scope. We looked at the organization that is, we organize requirements into operational, system, performance, and components. Operational requirements are described by what needs to be executed within the scope of the operations. System level requirements are more focused on the system and how it performs the operational environment. Performance level requirements are stated as required outcomes of the system action, typically stated in terms of engineering characteristics. And component level requirements are focused on the technical aspects of the system and will at a lower level of technical detail. In terms of requirements, metrics are used to inform the analyst, engineer, and decision makers whether or not the system will successfully accomplish its intended objectives while in an operational environment under operational conditions. And MOE refers to a qualitative or quantitative metric of a system overall performance that indicates the degree in which it achieves its objectives under specified conditions. And MOE always refers to the system as a whole. And MOP refers to a qualitative metric or qualitative metric of a system's characteristics or performance of a particular attribute of a subsystem. An MOP typically measures a level of physical performance below that of the system as a whole. In terms of requirements verification and validation, performance requirement validation involves two interrelated activities. One, integration of requirements derived from alternative system concepts, and two, effectiveness analysis to demonstrate satisfaction of the operational requirements. Performance requirements are defined in a living document. Requirements are reviewed and updated throughout the system lifecycle. And finally, the requirements development, TSE versus Agile. Traditional waterfall techniques may progress through a more methodical approach towards requirements development, but may take longer. Agile techniques may iteratively develop requirements quicker. Okay, well, that finishes up for this chapter. Thank you.